Greetings everyone, this is Mr. Mull and I'm going to help you navigate through some of this forces practice number 5, talking you through the solution to the first problem and giving you some hints on the second ones. You'll notice at the top of my worksheet I have written down the equations. Remember, friction is fun. If you can remember those equations, it's going to help us as we solve these problems. So as I move on to look at this problem, I'm going to go ahead and start by reading the question. It says, draw two quantitative force diagrams for the block, one while it is still at rest, but right before it starts to move, and one while it's moving at a steady speed. So I'm going to go ahead and do that first and show you my two force diagrams here, part A and B. So looking at my object, zoom out a little bit, I look around my object and look at the forces. So if you notice at the bottom left here, I have my normal force and my force of gravity. I take my 3 kilograms, multiply it by my 10 newtons per kilogram, giving me my 30 newtons of force. So you can see my diagrams filled out for those two. And then it says in the problem, it takes 6 newtons to start the block moving. So notice I have force of tension 6 newtons, and then a force of static friction was also 6 newtons. And that's because right before it starts moving at that instant, when it's still at rest, that 6 newtons is what kind of broke those bonds and started to move it. So that was our static friction. Then notice I drew a force diagram for the other one, the constant speed one. This is my second diagram here. And if you look at that one, the only thing I've changed differently is now that the force of tension is 2 newtons less and the force of friction is now 4 newtons. So there's option A. Looking at part B, it says what is the coefficient of static friction between the block and the table? To find the coefficient of friction is really easy. If we look at our original equation and rearrange it to solve for our coefficient, I've rewritten it here. All we have to do is divide out our numbers. So I look at the coefficient of friction. I want to solve for it. I'm just going to plug in those values that we found. Really as simple as just plugging in 6 newtons divided by my 30 newtons. And that's going to give us our coefficient of friction here. For this one, it is 0.20. Coefficient of static friction here. And then doing the work for the other one, it's going to be 4 newtons divided by 30 newtons, which is going to give me a coefficient of kinetic friction of 0.13. A little bit of rounding there. So now we found our coefficient of friction. Part C, it says we've solved that now. Part D, it says the block is then pulled with a steady 7 newtons of force. Draw a force diagram for the sliding block. So now what we have is a situation where we're pulling harder than friction is going to be able to pull back. That kinetic friction depends not upon the fact that we're accelerating, but it depends upon the normal force and the coefficient of friction. So we've solved for that coefficient of friction. We don't need it anymore. We need to look at the force diagram. So I look at this force diagram and I notice that the force of tension is 7 newtons. And I need to find the acceleration of the block, so we need a net force. So I take a net force, I make an equation. Force of gravity and force of normal are going to balance in all 3 of these situations. So the only unbalanced forces are going to be on the horizontal direction. Force of tension minus the force of friction. I plug those numbers in, the net force is 3 newtons. So once I've found the net force, I can then go back and find the acceleration using my Newton's second law. So I plug that in and I get a final answer of 1 meter per second squared. Now this was a pretty simple problem. We're just solving for the coefficient of friction. We're not really using it yet. We're just solving for acceleration, and we didn't need to use that. As you go through this, some hints for other questions. Number 2, you're going to have to find the frictional force, and so you're going to need to use your coefficient of friction, and you're going to have to find that first. Once you found that, you can find the frictional force using a net force equation. For this one here, you're going to have a lot of forces involved. Make sure that you break things into components that are not on your axes. You're going to need to do that. You're going to need to have a little ftx and fty. There's some hints on that one. Moving on to question number 4. I have a hint for part B. It says, what is your system? You need to find the acceleration of the blocks. For this problem, you're pushing multiple blocks. So if you think of those blocks as being together, their combined masses as an accelerating system, and notice I put a blue line here, you're going to be able to take the combined mass and find the acceleration of the overall system. Once you've done that, then you can go back through and do force diagrams for each of the blocks, and I will give you a hint that Newton's third law is going to be helpful when you're trying to deal with these different forces at the interaction of A pushes on B and B pushes back on A. That applies to both 4 and 5. And then questions 6 and 7, we're dealing again with things that are on an angle, so don't forget to draw a dotted line for the surface, or you could even draw right on that diagram, and you're going to make sure you're breaking into components those things that are not on your axes. So you're going to have an FG parallel, FG perpendicular. You're going to need to use some trig. Okay, there's our angle there. Alright, well, this is a very brief intro, and I hope that this was helpful. We'll see you